Like discrete random variables, continuous random variables have expected values and variances also. So for a continuous random variable, let's say x with probability density function little f of x, we define the expected value of x to be the integral from negative infinity to infinity of x f of x dx. So this looks a lot like the discrete definition, where we have x times probability of capital X being little x. And that's not an accident. This comes from Riemann sums and the limit of the sum of x times probability that capital X equals little x. Similarly, if we have a function g of one variable, we have the expected value of g of this random variable is a similar integral where in place of x we have g of x. So for example, let's let capital X be an exponential random variable. Let's say it has parameter lambda. Let's find the expected value of x, the expected value of x squared, and variance of x, which is expected value of x squared minus expected value of x, the whole thing squared. Right, so the density of the exponential random variable is lambda e to the minus lambda x, at least for x greater than or equal to 0, and it's 0 otherwise. So that means the expected value of x is the integral from, we can just say from 0 to infinity of x times lambda e to the minus lambda x dx, because that integral from negative infinity to 0 is just 0. Alright, so we have an improper integral, because one of the limits of integration is infinity, and we need integration by parts to do this because the x times the exponential. So I think I'm not going to do the integration by parts out on the board. But after we do integration by parts, we have the limit as b goes to infinity, so that'll be for the improper integral. Negative lambda x plus 1 over lambda e to the lambda x in the denominator, evaluated from 0 to b. So this is the limit as b approaches infinity of, let's plug in b, plug in 0, and then subtract. So minus lambda b plus 1 over lambda e to the lambda b minus negative lambda times 0 plus 1 over lambda e to the lambda 0. As b goes to infinity, e to the lambda b goes to infinity faster than lambda b. So this thing goes to 0. And then that leaves us with 0 plus 1, 1 over lambda times e to the 0th, which is 1, so 1 over lambda. All right, now the expected value of x squared is the integral from 0 to infinity of x squared lambda e to the minus x, e to the minus lambda x dx. Again, this is an improper integral because of the infinity here, and we need integration by parts twice because it's going to take 2 integration by parts to get this x squared down to a constant. Now this took me a page and a half, so I think I'm not going to show you all the integration by parts, especially because there's a negative exponent, which is just sort of nasty for integration by parts. But if I show you what I got after integration by parts, it is negative lambda squared x squared plus 2 lambda x plus 2 all over lambda squared e to the lambda x. So this whole thing evaluated from 0 to b. Oh, I left out the limit. So we'll plug in b, plug in 0, and subtract. Lambda squared b squared plus 2 lambda b plus 2 over lambda squared e to the lambda b minus negative lambda squared times 0 plus 2 lambda 0 plus 2 over lambda squared e to the lambda times 0. So we still have this e to the lambda b in the denominator, which is going to go to infinity faster than anything in the numerator here, even though b goes to infinity. So this is all 0. And then in this expression, that's 0 plus 0 plus 2 over lambda squared e to the lambda times 0, which is 1, so lambda squared. All right, that's e to the x, expected value of x squared. Now, variance of x is the difference between expected value of x squared and expected value of x, the quantity squared, which is 2 over lambda squared minus 1 over lambda, the quantity squared, so 1 over lambda squared. So 2 minus 1 over lambda squared is 1 over lambda squared, so that's the variance. Now, let's just do one example. Recall that if x is a Poisson random variable, then the waiting time between occurrences is an exponential random variable, y exponential with parameter lambda also. So suppose lambda equals 1/2. So we did an example where typist makes on average 1/2 typos per page, which we could also say is about 1 typo every 2 pages. So the exponential random variable would be space in between 2 typos. So the expected value of y is 1 over 1/2, which is 2, which is exactly the same as what we said when we rephrased the typist makes an average of 1/2 typos per page. We said that's 1 typo every 2 pages, so we'd expect about 2 pages between typos. The end.